So if you're looking at this, they are talking about how many millions of households only have wireless phones. They do not have a landline. And they've given us this function to represent it, and the graph as well. So this is the function. It says, state the relevant domain and approximate the range. So domain, you can tell that it goes from 0 years, obviously, since 2001 until, I mean, it's going to go on indefinitely if they keep tracking this, but eventually it's probably going to just plateau out where nobody has a home phone at some point. And then it says, use the graph to estimate the number of households with only wireless phone service in 2003. All right, so if we're looking at this and it is since 2001, year since 2001, then which one of these numbers down here represents 2003? Two. All right? 2, because you're going since 2001. So if you approximate this, you may have said close to 5 million maybe, or like 4.8 million, because these go up by 2s, right? So if you're approximating it, whatever your approximation was here, as long as you were here, not here. All right, so you're going to be in the 4 million range, 4 to 5 million range right there. Use the graph to approximate the y-intercept of the function. Then find it algebraically. What does the y-intercept represent? All right, so my y-intercept is right here. Just looking at it, since this is every 2, this is probably around what, 1.2, 1.3, somewhere in there, just looking at it. Algebraically, I would plug in a 0 up here, and it would be 1.2, right? So algebraically, I get the exact, it's 1.2 million. What does it represent? Well, if I am on this axis, it means this is 0. So it represents how many households had it when? In 2001, when I am 0 years away from 2001. So on the y-axis, it is when this one is 0. If they wanted the x-intercept, which we don't have one, then it would be when there were no households with only cell phone service, which they'd have to go back further than 2001 to do that. Since we're starting in 2001, we don't have an x-intercept. Does the function have any zeros? I just answered that question. No, zeros would mean an x-intercept. This particular function does not have an x-intercept. Explain why. Well, they started in 2001. Apparently in 2001, 1.2 million households already only had wireless service. All right, so we're thinking like 20 years ago. I can only imagine how much that has gone since then. All right, so we're going to talk about continuity in behavior of graphs. Continuity just means continuous. Is it continuous? Continuous in graphing really means the same thing in anything else, right? If something is continuous, it keeps going, right? It's not rhythmic. Rhythmic means that it goes and stops and goes and stops, right? Continuous means it continues and keeps going. The example they give us first is federal minimum wage. It says the minimum wage has increased significantly since the early 1980s. Rather than increasing steadily, the current minimum wage is a result of several jumps. All right, so why would this function look like this? Well, because they don't go from $4 to $4.01 to $4.02 to $4.03 to $4.04 to $4.05 for minimum wage, right? In fact, in like the 1980s, it was really low. What was it, like $3.25? It looks like here. All right, and then it jumped to $3.75, and then it jumped to $4.25, and it stayed there for a period of time, and then it jumped to $4.75, and it stayed there for a period. And so with minimum wage, what it does, and I think now it's what, $7.25, some up here now. So with minimum wage, it jumps. This is actually a jump function, step function, where it stays. This is technically the type of function this is as a step function. You can see it looks like steps. It stays for something for a period of time, and then it jumps to another level, and then it stays there for a period of time, and then it jumps and stays. And jumps and stays. This is not a continuous function. You can see that, right? For a continuous function, I literally should be able to take my pen and draw without picking my pen up and stay on the function. Well, I cannot do that. It's not continuous, all right? And so let's talk a little bit about what that means. Continuity. And so they define this for you right there at the top of page 24. It says the graph of a continuous function has no breaks, no holes, no gaps. You can trace it without lifting your pencil. One condition for a function to be continuous at x equals c is that the function must approach a unique function value as x values approach c from the left and the right. This value is called the limit. So we have two things here with continuity. First of all, is it continuous? It keeps going. Second of all, they use this term limit. All right, and what they'll do is they'll pick a point just anywhere on the graph, and they'll say, is it continuous here? And what you're going to look at is it defined there? And am I going towards that number from the left and the right? And so if you were to take from the left and from the right, then you would say, yeah, it's continuous at this particular point because I can go from the left and the right and I can see what it's doing. All right? So this is a continuous function. So the functions that we've dealt with, linear functions, those are continuous, right? They go on infinitely, there's no breaks. Parabolas, your x squared, your quadratics that we've looked at, those are continuous. It's that U shape and it keeps going. Even absolute values are continuous, right? The V shape of an absolute value, continuous, right? It does turn, but there's no break in that graph. And so we've looked at a lot of continuous functions. What we're going to look at in this section is ones that are discontinuous, ones that actually have breaks in the graph. And so if you look, they give you types of discontinuity. Types of discontinuity. The first type of discontinuity is an infinite discontinuity. It is called this because, as you can see, we have a break in the graph right here. And at that break, it goes to infinity. Goes to infinity here, goes to infinity here. So at the break, your function shoots off towards infinity. It doesn't have to go opposite directions. It can actually go the same direction. You can actually just have a jump in between them. But this is an infinite discontinuity, meaning that your graph shoots off to infinity when you get to that particular point. The next type is called a jump. This is from the example they gave us on minimum wage. That's a type of jump. This one will be created from like a piecewise function, like the ones that we did where you had to pick which one you could plug it in for. This is what a piecewise function will look like. They'll have some definition of the function. This is a linear function here up until this point C. And then they'll say, well, greater than C, now use this function. And so you plug in that function to figure out what it is there. This is a jump. Easy to recognize. Why? Because it looks like you jumped, right? Looks like you jumped from functions. All right, and then the last one is point discontinuity. Point discontinuity, again, looks exactly what it sounds like. At this point, it is discontinuous. So here we have discontinuity. This is a hole in the graph. It is point discontinuity. All right, so let's look at how we figure out what we have. So it's really easy to figure out what we have when we have a picture, but when you don't have a picture, how do you know what you have? And so let's look at the types of discontinuities. All right, so for the first one, it says a point discontinuity is called a removable discontinuity. All right, if you were to look at the function, then there is something you can do to get rid of your problem. All right, so discontinuities are caused by problems. We've looked at problems with domain. Zeros in the denominator, that is a problem, right? A negative under a square root, that is a problem, okay? And so there are times when you can maybe factor out your problem and get rid of it. That will be a removable discontinuity. Removable. So that means you can take out your problem, but your original function still has it in it. So you'll be able to graph it, but you're still going to have this hole that's created, all right? So removable discontinuities create holes in the graph. If it is removable, it creates a hole. You're going to need to know that because I am going to ask you, what type of discontinuity do you have? And you're going to have to tell me removable. I'm going to say, name the holes in your graph. And you're going to have to go, oh, holes, that means removable. Okay. And so you need to know that removable discontinuities create holes in your graph. All right. Non-removable discontinuities. These are two types. Okay. Non-removable creates one of two types. It creates a jump. That will be with like a piecewise function. All right. If it is not a piecewise function and you have a discontinuity that you cannot remove, then it creates what's called an asymptote. And we're not going to graph these yet, but these are these dotted lines that you get infinitely close to, but you never actually touch. And so with infinite and jump discontinuities, those are non-removable. Non-removable. You can't get rid of them in the function. And so something happens there that you can't get rid of. All right? So let's look at the examples here. Continuity test. Look at the middle of page 25. How do we know if it's continuous? This is the former definition of how we know it's continuous. You can look at it and tell, right? But then if you just have the function, how do you know? The first thing is that at the point they're talking about, you can actually have a point and plug it in. All right? So can you just plug that point in and it give you a number without any problems? If that's yes, then you're on your way to continuity. The other thing you're going to look at is if you go from the left and the right, are you coming towards that point? That is the limit as it goes towards that point. And so if those two equal what you're going towards and what it is defined at, then you have continuous. When would this not work? Well, let's look up here at this example at the very top right here. All right. So first, this particular function, do we have a definition at C? Do we have a y value at C? Yes or no? Is there a y value at C? Yeah, it's right here. See that point? So if I plug C into this particular function, I'm going to get this point. So that meets the first definition. If I plug in C, I get a point. That is true. If I'm approaching left and right, am I approaching the same number from left and right? Well, yeah, from left, I'm approaching this little hole, and from the right, I'm approaching this little hole. Yes? So it has a limit at that point as well. It is defined at that point. It has a limit at that point. So far, so good. The third one, does the definition at that point and the limit at that point equal? No. When we plug it in, we get this number. When we look at what that graph is approaching, we get this number. This is not continuous, and you can visually see that. You can see it's not continuous. I have a hole in my graph. We have a problem. All right? So that's what continuity means. Is it continuous without a break? Visually, it's very easy to see. Algebraically, you need to deduce that from things that you're looking at. So let's look at this particular example. All right? Let's look at this example. They did not give us a graph. Determine whether this function is continuous at x equals 2. Justify it with the continuity test. So first of all, I'm going to look at this. What type of function is this? Think about what the graph looks like. This is a quadratic. All right, so remember your quadratics. You had to graph them for me, did you not? You had to graph your axis, your vertex, then you had to graph your y-intercept. And what did the picture look like? What is that called? That's a mx plus b, y equals mx plus b. Quadratics do this little guy.
The parabola.
It's a parabola, all right? So just mathematically, if I were not to say prove this, hopefully you would look at this guy and say, well, that's just a parabola. Parabolas are continuous. That's a parabola. I know this is a continuous function because I have had to graph these. They are continuous, all right? So just knowing it's continuous kind of helps you know where you're going, recognizing the function. So then it says prove it. So what we're going to do is we're going to do those 3 steps. We're going to say, does f of 2 exist? Well, yes, it does. So I'm going to actually plug in f of 2. What does that mean? We just did this. What does it mean when it gives me this notation here? Plug it in. So I say 2 times 2 squared minus 3 times 2 minus 1. Okay? I'm plugging it in. 2 squared is? Times 2 is? Minus? Minus 1? Yes. All right. So what do I get there? 1. All right. I get 1. Now what they've done to see if the limit exists, I'm actually not going to make you do these charts because they just take forever. But I want you to visually see it, all right? So what we're going towards is 2. So they didn't pick like 1, 0, -1, right? They want something t-tiny close to 2. So they did 1.999, 1.99, 1.9, and then they did 2.001, 2.01, and 2.1. And they plugged those into the equation. And so as you see this progression, can you assume, like if this were on a standardized test and they would say, what do you think this is approaching? What do you think this number is going to be? Well, it looks like it's going towards what? 1, right? So the limit of this guy is actually going to be 1 as well, right? And so what they're asking down here is, does the limit, what is approaching, equal how it is defined? And yes, the answer is yes. We got a 1 here, and when we look at this chart, we get a 1 there. That means this is a continuous graph. So even if we did not know that this was a parabola, we could look at those 3 things and we could say, yeah, this is continuous. There's no breaks in the graph. All right, charts. The first one, x cubed. All right, so they want us to know if it's continuous at 0. So f of 0, that's going to be 0 cubed, which is 0. All right? If we were to plug in, so get your calculators out. We're going to do this together so that everybody doesn't have to do. For 0, we are going to use small numbers away from 0, okay? So like over here, we would say 0.001, 0.01, okay? And on the other side, we would use something like negative, right? And you want to get close to it, so you're going to say negative 0.001. I'm going the other way. Negative 0.001 and negative 0.01, something like that. All right, because we're going these directions. So what happens when I plug in 0.001? What happens there? What is that cubed? It's going to be this crazy. Yeah, it's going to be this guy. We should have 9 decimal places, if I'm counting correctly, something like that. This guy's going to have 4 decimal places, right? This is going to be the same thing on the negative side, isn't it? And negative. So if I were to say, what is this approaching? We're definitely approaching 0. Those 2 guys are getting infinitely close to 0 is what's happening there. So then I'm going to say, do these 2 equal? Well, yeah, 0 equals 0. So yes, this is a continuous function. That's easy. Okay? Yeah, it's a continuous function. All right, the next thing. This is a jump function, but it could meet. Jump functions can meet, okay? So we're going to just evaluate this at 0. Which one am I going to use if I want it to be equal to 0? This one. Why? Because it's greater than or equal to 0. So I'm going to use f of 0. That is just 0. Everybody see that? So how do we know if it's approaching those things? Well, we plug it into both pieces of it, even if it's not part of it. So I'm going to take this and I'm going to actually plug it into the top one. 1 over 0. That is undefined.
0 can't be the denominator. That's weird. That's wrong.
Right. So these two do not equal. These don't equal. So no, this one is not continuous. All right? This one is not continuous. Here's what you'll typically see from me. You're going to get a function, and I'm going to say, is this continuous, yes or no? If it's not, tell me what type of discontinuity you have, okay? So let's look at the piecewise function here. They want to know, is this continuous at x equals -3, all right? Is it continuous at x equals -3? So how we're going to determine that is we're going to plug in -3 to both pieces. All right, so we're going to say 3 times -3 minus 2. All right, that's what it's approaching from the other side. 3 times -3 is what? -9, right? Minus 2 is -11, right? -11. All right, and then what we want to do is we want to determine what it is when we plug it in. 2 minus -3, that's going to equal what? 5, all right? So from those two, we're going to determine this is not continuous, all right? This is not a continuous function because on the right-hand side of x equals -3, that function is going towards -11. But when we actually get to -3, it jumps to +5. And so if you look at the graph in your book, you will see that as you're going towards -3, from the left-hand side, it looks like it's moving towards -11. But as soon as you get to -3, it jumps off and it looks like a new graph here. Looks like a new graph. All right, so if you look at this guy right here, you can see from the right side of here, from bigger than -3, as it's moving towards -11. You can see that. But once it actually gets to -3, the graph jumped up to +5. That's what plugging it in told us. Plugging it in told us, okay, for this, as it's going towards -3, it's moving towards -11. But because they changed the definition on me right at -3, when I get there, the graph jumps to +5. So this is discontinuous. I know that. All right. What type of discontinuity? Well, this is a non-removable. So it's either an infinite or a jump. All right. In this case, it's a jump. It literally goes from -11 and it jumps to +5. So this is going to be a non-removable, which means it is either a jump or an infinite. In this case, a jump. This is a jump. Okay? Let's look at the next one. All right, they want to know what happens then at -3 and at +3. So let's first plug it in and see if it's even feasible. Can I plug it in? -3 squared is 9. 9 minus 9 is, we have a problem, right? 3 squared is 9. 9 minus 9 is also 0. So neither one of, it's not continuous at either one of those. We already know that just plugging it in, it's not continuous. It's not going to be continuous. So now what we're going to do is we are going to then say, is it removable? Well, what do I mean by that? So when it causes a problem in the denominator, factor your denominator. All right. This is a special case factoring. How do I factor as squares? 2 squares. Yeah, it's plus minus. Y'all remember that? When you have a squared minus b squared, the factoring is a plus b, a minus b. All right. So I can factor this. My numerator looks like that. My denominator looks like this. All right. Everybody see that? Do you think one of those is removable? Why? You can cancel them, right? And so I have a removable discontinuity. This guy right here, you can remove him. What did I say a removable discontinuity causes? A hole. So at which of those numbers causes a problem here? Positive or -3? -3. So at x equals -3, I have a removable, and it is a hole. I have a hole. So in this graph, I'm going to have a picture, and it's going to have a hole in it. All right? It's going to have a hole in it. All right? What about the x minus 3? Can I remove it? I cannot. All right? I cannot. So which number causes the problem there? That's +3. So at x equals 3, I have a non-removable. And this is actually not going to be a jump, but we'll actually get to how to graph those later. You can put non-removable. That's non-removable. That's actually an infinite, all right? So when it's non-removable, but it's not a jump, we are going to say this is an infinite. An infinite, okay? So we have one hole and we have one infinite discontinuity, all right? Questions on that? So I want you to try one. So go to the bottom of page 26. All right, let's look at these. Does 0 cause a problem for the first one? Yes, so if I plug in a 0 here, I get 1 over 0 squared. This is a problem. We can't have a 0 in the denominator, okay? So I know that this is going to be discontinuous, right? Right away, I already know the function is not defined at this number, okay? So it's not defined there, so f of 0 just doesn't work. Does not exist, okay? Doesn't exist. So then I'm going to say, can I cancel it out? Can I remove it? Can you remove this? Is there anything you can cancel that x squared with? No, I cannot cancel the x squared with anything. So this is non-removable. All right, which means this is non-removable and it's not a piecewise function. So this is going to be an infinite discontinuity. Infinite discontinuity. Infinite. All right, let's look at the next one. Is this defined at 2? Well, yes. It gave me what I can do at 2 here, right? So at 2, I would plug it in to my bottom function. 2 minus 2, and I am going to get 0, right? Then my next question is, well, is it approaching 0 when I go from the other side, right? Is it approaching 0? To find that out, we're going to plug it in here to see what it's approaching. So we're going to say 5 times 2 plus 4. That gives me 14. No, it's going to be approaching 0. It's going to be approaching 14 over here. But once we get to 2, it's going to jump to 0. Does everybody see that? It's approaching 14 up here. But then once I get there, it's going to jump to 0. So this is also non-removable. But this is a jump discontinuity. All right? Questions on that one? The last thing you can glean from a function is what's happening at the end of it. All right, what's happening at the end of it. When it is an infinite function, it'll go on infinitely, either positive infinity or negative infinity, okay? So if it's an infinite function, you're gonna have arrows at the end. And you can actually look at the function and figure out what's going on with it. All right? For some reason, they break it up. And in this chapter, they just talk about it. And in the next chapter, they give you a shortcut. I'm gonna go ahead and give you that shortcut. I don't want you to be graphing these. All right, there's a shortcut. You can actually look at your highest exponent, right? Your highest exponent, and you can look at your coefficient in front of that guy. All right. If your highest exponent is odd, if it is odd, the function will go different directions, meaning one side will go to positive infinity, one will go to negative infinity. Always. That's how it always will be. So these are both odd, meaning they have like something like, this has like 3x cubed at the beginning, and this has negative 3x cubed at the beginning. All right? And so if it is positive in front of it, that's odd, it's going to go to negative infinity on the left here, and it's going to go to positive infinity. So basically, it's going to always be going up. All right? So if it is an odd, and it has a positive number, it's always going to be going up, down on the left, up on the right. If it is odd, but your coefficient's negative, it's going to continually be going down. So on the left-hand side, it's positive infinity, and on the right, it's negative. It's constantly going down. All right? That's what it looks like when you have an odd. Even. So this would look like, give me 1 second, this would look like 3x squared, negative 3x squared. When it is even, it will go the same direction. Up if it's even with positive, down if it's even with negative. And so that shortcut will work for any of your polynomial functions here, any of your polynomial functions.